All right, folks, welcome to the vasculature, blood vessels, and circulation. So this is the last chapter covered before the next exam. Your next exam will be the cardiovascular system, chapters 19, 20, and 21. So let's talk about the blood vessels. Well, previously in the heart chapter, I had mentioned that the blood vessels were just plumbing, and the really important things that went on in the capillary bed. Now, I was being a little bit simplistic in that statement because there's certain things happen in this plumbing that can cause disease, and we have to talk about some of these. So when we look at the blood vessels, we have three basic types of blood vessels. We have the arteries, which always carry blood away from the heart, and you can see here that the arteries are moving away from the heart. They're colored red typically because they're showing that they're oxygenated. Now there are a couple of exceptions to that rule. You already know about the pulmonary exception, and I'm going to teach you the fetal exception today. So you can see these arteries. We have these big elastic arteries. We do have a lot of smooth muscle here in the tunica media, but the elastic arteries are so big that contracting the smooth muscle in the tunica media doesn't overall change the peripheral resistance as much as the muscular and arterioles are going to. After the elastic arteries bifurcate, we have these muscular arteries here. And the muscular arteries, similar to the elastic arteries, have a lot of smooth muscle in the tunica media, but they're lacking the internal and external elastic membranes that you saw up here in the elastic arteries. You can see this internal elastic membrane right here, and likely there's actually an external elastic membrane as well. It's not shown here, but there could be. And this muscular artery is lacking that. Then when the muscular arteries bifurcate, we're down here to the arterioles. These guys are the resistance vessels. And the reason why we call these guys the resistance vessels is because all of this smooth muscle around the arteriole, when it contracts, it vasoconstricts and increases the resistance of peripheral blood flow. And changing the resistance in the peripheral blood flow has a huge effect on where your blood goes, as you'll see here shortly. And the other reason why this is the major area of resistance is because the overall cross-sectional diameter, that means the diameter across the lumen of this arteriole, overall the cross-sectional diameter of the arterioles far surpasses the cross-sectional diameter of the muscular arteries or the elastic arteries. Now you're going to say, how can that be? The elastic arteries are big and the muscular arteries are bigger than arterioles. I agree, but there's far more arterioles than there are muscular arteries and elastic arteries. And if you add up the cross-sectional diameters of the arterioles, they far surpass overall the cross-sectional diameters of the muscular arteries or elastic arteries. So by contracting these smooth muscles and vasoconstricting the arterioles, you change the peripheral resistance a great deal, and you can therefore change blood flow. From the arterioles, we get into our capillary beds here. We have an arterial side of the capillary bed, and we have a venule side of the capillary bed. Matter of fact, this venous side is called the venous capillary, and this arterial side is called the arterial capillary. There's three flavors of capillaries. There's sinusoidal, fenestrated, and continuous. You can see that we have two of those represented right here. Continuous capillaries and fenestrated capillaries. We have another kind that is found in the liver and the spleen, and it's called sinusoidal capillaries. It's they're really a modified type of fenestrated, but the fenestra are very large. So we have these sinusoidal capillaries that we'll talk about. So three types of capillaries. This is where gas and nutrient exchange is going to occur. The capillaries are one cell thick. The endothelial cells are the only cell that is between the blood and the interstitial fluid right here. There is a basement membrane still, but they're only one cell thick. There's not a tunica intima, tunica media, and tunica externa. There is only a tunica intima. And we don't even name it that because it's only one layer. So there's only the endothelial cells, and that's it. Many of the capillaries start fusing together to make these venules. See this word venule right here? And going back towards the heart, these venules and veins, uh, similar to an artery, have a tunica intima, tunica media, and tunica externa. However, the smooth muscles in the tunica media are far thinner in veins than they are in arteries. So we have these venules, then we have these medium-sized veins, then we have these large veins. Not shown here, but one of the biggest differences is veins have valves. Arteries do not have valves. So that's one of the biggest differences. All right, so that's the in general blood flow. Now we're going to modify that a little bit. We're going to talk about portal veins and afferent and efferent arterioles, but it's basically this plan, just modified slightly. This is showing you the histology of a blood vessel, and we're going to do this in lab. I'm trying to think what lab we had last week. So we're definitely going to cover this in lab. We cover the histology. And you have a tunica intima. So right here's the tunica intima. It's the endothelial cells in the basement membrane. That's what that is. You have the tunica media, which is your muscles, your smooth muscles throughout the surrounding the blood vessel. And then you have the tunica externa right here. Now here's the deal. If you're a big artery, you are likely to have an external elastic membrane, and that would be right here between the smooth muscle and the tunica externa. And you could even have an internal elastic membrane, and that's right here between the tunica intima and the smooth muscle. And the big arteries have those elastic membranes. Now, let's look over here at a micrograph of a blood vessel. The veins are typically large when I look at the lumen. And the arteries, in relation to the veins, now you have to compare apples with apples. You have to compare large veins. Let me go back and show you. You have to compare large veins with elastic arteries, or you have to compare medium veins with muscular arteries, or you have to compare venules with arterioles. But if you do compare apples with apples, you will see this. You will see that the vein has a very large lumen and the artery has in relation, smaller lumen. But you'll see that the wall of the artery is much thicker than the wall of the vein, and that's because of that tunica media. So that's an artery and a vein. At any given time, most of your blood is in the veins, and that might not make sense right now, but I will explain that statement in a bit. So that's the histology of your vasculature. Some more histology right here. All right, this is showing you the three types of capillaries, and continuous capillaries mean that there's tight junctions here. So in these boundaries between the endothelial cells, there's tight junctions. So it's very difficult for things to get out of there. Now I will tell you this, that we do change those tight junctions. We've transiently change them because white blood cells squeeze through there. So it's not like that tight junction is like the blood-brain barrier where nothing gets through. And actually, even with the blood-brain barrier and the blood-testes barrier, those tight junctions aren't perfect either. So we do have tight junctions which it's difficult for things to get through. However, some white blood cells can squeeze through there, and that has a name, and I'll tell you in a few minutes. So these are continuous capillaries. Be very difficult for things to cross that membrane. They have to go through the cell. Now gases exchange very easily across that membrane. So O2 and CO2 very easily cross those membranes. Other things might have some active transport mechanisms to cross those membranes, but going in between the cells would be difficult. With fenestrated capillaries, you have these fenestra or windows right here. And these fenestra or windows or pores, fenestra really means window, but your book's calling it a pore, which is fine. These are areas where things can get through. And when you say, well, what kind of things? Like macrophages, like filtered substances. We have these fenestrated capillaries in our kidneys. Well, what do our kidneys do? They filter blood. So we're talking about fenestra here. Now, some of these fenestra, let me see if I can remember the size of them. They are about 90 nanometers. Not very big, 90 nanometers. But big enough to allow proteins through. I mean, albumin's probably about 8 nanometers. Albumin's one of the smaller proteins. It's about 70 kilodaltons. Don't worry about what a kilodalton is, but albumin's one of the smaller of the proteins. It's only about 8 nanometer diameter. If you look, it's a globular protein. It's hard to give a diameter to it, but let's say it's 8 nanometers. So that albumin could very easily fit through that fenestra. But when we do talk about the kidneys later in your life, we will talk about why albumin doesn't ultimately make it through there, even though it could fit through the pore. So these fenestra are about 90 nanometers. And then you have a type of capillary called the sinusoidal capillaries. It just means that the fenestra, well, a couple ways of looking at it. You could say that the endothelial cells aren't tightly attached, and that's probably the most accurate way. There's great big gaps between adjacent cells. Another way of looking at it is the fenestra are huge, and it's just a subtle difference between looking at it one way or the other. But you can see these big gaps. There's two places that sinusoidal capillaries exist. It's in the liver and in the spleen. By the way, there might be a couple other minor places as well. But the liver and spleen have sinusoidal capillaries, and it lends to their function and to the function of what they do for us in the immune system. All right, those are the three types of capillaries. Just some words here. Vasoconstriction is contracting the smooth muscle in the tunica media and makes your cross-sectional diameter smaller. And that increases peripheral resistance. That increases the resistance of blood flow. Vasodilation is by the way, did I just say that backwards? I should have said this. Vasoconstriction is making the cross-sectional diameter smaller. Vasodilation is making the cross-sectional diameter bigger. When you make the cross-sectional diameter bigger, you decrease peripheral resistance. When you make the cross-sectional diameter of the lumen smaller, you increase peripheral resistance. And we'll look at that and the effect that has. The effect of vasoconstricting and vasodilating is affecting the afterload on the heart. Let me remind you what that means. You had a preload, a contractility, and an afterload that we looked at on the heart. The afterload on the heart is the amount of tension the left ventricle must produce to push blood into the aorta. Now, the higher that afterload means the less easy the blood goes into the aorta. And that has to do with how constricted or narrowed is that aorta. And downstream from the aorta, not just the aorta and aortic arch itself, but downstream too, because if you make it very difficult to move the blood through the descending aorta and the common iliacs and the femorals and et cetera, then that's going to increase the afterload on the heart as well. And remember how I said having a high afterload is not good back in the heart chapter? Well, if your arteries are all vasoconstricted, your heart's going to have to work very hard. And if it's a chronic condition, you could get a cardiomyopathy. You could actually get enlarged heart because it has to work so hard to push the blood out. The vasoconstriction or vasodilation affects blood pressure when you put the blood pressure cuff on and measure it. If you're chronically vasoconstricted, you're going to have a high blood pressure. If you're chronically vasodilated, you're going to have a low blood pressure. And capillary blood flow or perfusion. Capillary blood flow is something we call perfusion. It's getting blood to the tissues, which is the capillaries. That's where tissue exchange occurs. So vasoconstriction and vasodilation is going to affect perfusion. Typically speaking, when we're vasodilated, we have great perfusion. It's very easy for the blood to flow through there. It might not be under high pressure, but it flows easy. And when we have vasoconstriction, we have lower perfusion because it's harder for the blood to flow through there. It might be under high pressure, but it's less flow. All right. This is showing you a capillary bed, and you have to know this for the test. I have a picture of this on the test. So we have, let's go through here. We have these arterioles right here. Oh, actually, let's say these are collateral arteries. That's what the book's calling them. So let's call them collateral arteries. They become arterioles You can see these arterioles surrounded by smooth muscles. These smooth muscles could vasoconstrict and increase resistance, or vasodilate and decrease resistance. Then these arterioles branch into these meta-arterioles. This is a meta-arteriole. This is a meta-arteriole. These meta-arterioles is the beginning of your capillary bed. And then you have your capillaries in here. All these are capillaries. It's really where the red and the blue are kind of mixed. We have the arterial side of the capillary and we have the venule side of the capillary. This is where exchange is going to occur. Now, let me just give you a statement here. You do not have enough blood in your body to fill all the capillaries in your body. Now, that should be a confusing statement, because if that's true, if you don't have enough blood in your body to fill all the capillaries in your body, you should have no blood pressure. You should have partially filled capillary beds and absolutely no blood pressure whatsoever. All the blood should be pooled in your capillaries, and you still don't have enough to fill them. But that's not the reality. The reality is your blood pressure's fine, and your blood fills your arteries and veins. So how can that be true? How can that statement be true if we're not hypotensive and dead right now? And the answer is, and you probably know the answer, is that we have these precapillary sphincters. Right here, precapillary sphincters. And when they contract, they shut off flow of blood to these capillaries. And you're going to say, well, where does the blood go? Well, it goes down through and hits a thoroughfare channel. By the way, the thoroughfare channel, it's called a thoroughfare channel, but it's also can be called an arterial venous anastomosis. An arterial venous anastomosis. All right. So the blood hits this thoroughfare channel and then hits the veins. Now, what you're going to say to me is, Kiggins, that area had no perfusion. And I'm going to say you are exactly right. But our body responds to needs. When tissues don't have a great need for oxygen because they're not actively metabolizing, there's a local autoregulation that contracts these precapillary sphincters and shuts down blood flow to that area. Why do you need blood flowing to the area? You have no need for glucose. You have no need for oxygen. You're not metabolizing and generating CO2, so you don't have any waste products. And if you don't have waste products, you don't need oxygen, don't need glucose, why have blood go to the area? And the answer is you don't. So at any given time, most of our capillary beds, more than half of them, are closed. But they vacillate or fluctuate between being open and closed. And when you're exercising, working out, doing some activity, you open the capillary beds to the muscles you are using. You close the capillary beds to the muscles you are not using. All right, so that's the precapillary sphincters. That's shunting blood through a thoroughfare channel. And that answers the question, how can you have such a huge cross-sectional diameter of capillaries, more than enough to hold all the blood of your body, and yet not die from hypotension? And the answer is you close down most of your capillary beds at any given time. Another picture, different picture than in your book. I just like to bring some alternate pictures in to show you that, to show you another viewpoint, really. That's all it is showing you another viewpoint. So you can see the precapillary sphincters here and here. If you contract those precapillary sphincters, the blood stays in this thoroughfare channel and goes right over to the venous side, likewise right here. Whoops. Yep, right there like that. So you'd have to shut down all these precapillary sphincters. If you open those precapillary sphincters, of course, the blood flows through the capillary. This is showing you a couple different types of circuits. The simplest pathway is the one that I taught you already that you're thinking about. An arterial becomes a capillary bed goes to a vein, and it returns to the heart. But we have, in a couple different places in our body, like between the hypothalamus and pituitary and in our intestines to our liver, we have a portal vein. What a portal vein is a vein between two capillary beds. So we go arterial to capillary bed, to vein to capillary bed, to vein. Well, what's that vein in the middle of two capillary beds called? And that answer is a portal vein. This is showing you an arterial venous anastomosis. Uh, I would say all of our capillary beds actually have this. All of our capillary beds have a way for the blood to get to the venous side if you were to shut down that capillary bed right there with precapillary sphincters. And then the bottom one is probably in reality how all of our capillaries exist. And you can see that we have collateral arteries fusing, we have arteries bifurcating, we have them becoming capillary beds, we have capillary beds fusing together to become venules, venules fusing together to become veins, etc., etc. This is probably the reality of most of our capillaries right there, because it's never as simple as it looks in the beginning. All right, so that's capillary beds for you in circuits. Angiogenesis is a word that means growing new capillaries, new blood vessels. Capillaries are blood vessels. This is a good thing and sometimes, and it's a bad thing sometimes. Well, when is it good? Well, part of athletic training is working out and angiogenesis. You actually grow new capillaries into your muscle tissues as you train. And this is why you see yourself getting better and better and better at running the 5 miles. Your time gets shorter and shorter and shorter. You're actually delivering more oxygen to those muscles more efficiently because you grew new capillaries into the muscles. So that's a great thing. So why is this bad? Well, cancer cells secrete chemicals, many of them, not every one, but many cancer cells secrete chemicals that stimulate angiogenesis because the tumor is going to grow very fast and it needs a supply of oxygen and glucose and other nutrients. So it secretes angiogenic compounds and you capillarize your tumor. In fact, some of our chemotherapeutic agents that help to kill a tumor are anti-angiogenic compounds that inhibit angiogenesis of the tumor. Now you're going to say, well, doesn't that inhibit angiogenesis of my muscles as well? Yes, it does. So you're probably not going to get the same results from exercising when you have cancer as when you don't, because you're taking a chemotherapeutic agent that inhibits angiogenesis. Vasomotion is, I've actually already said it, I just didn't use the word vasomotion. You know how you don't have enough blood in your whole body to fill all the capillary beds, but how can that be true? And the answer is we have our capillary beds at any given time, more than half of them are closed. Well, vasomotion is the fluctuation between opening and closing capillary beds. You open them when you need, when the tissues that are fed by that capillary bed need oxygen, and you close them when the tissues fed by that capillary bed don't need oxygen. And that's a constant back and forth, open close of precapillary sphincters, and that's called vasomotion. Now this goes back to Starling's law of the heart, back what I talked about in the heart chapter. This is just one example of many things that happen peripherally. What happens peripherally is all of this blood from the capillary beds is entering venules and veins and returning to the heart. And especially below the heart, it's going against gravity. Well, how the heck does that work? There's no pump behind the veins. The heart is the pump that pumps arterial blood. But by the time you get to the capillaries, all of that pressure has been dissipated because you have gone from a narrow lumen to overall a huge lumen. And when I say overall, you'd have to add up the cross-sectional diameter of every single capillary, and it's a huge lumen now. So you've lost all that pressure. Well, how do we get blood back to our heart if the venous blood's not under any particular significant amount of pressure? And the answer is skeletal muscles act as pumps. So this is showing you the gastrocnemius contracting, and it pushes on this deep vein right here. And when it pushes on this deep vein, it pushes the blood upward. Now you relax your gastrocnemius. How come the blood doesn't flow back downward with gravity? Because we have valves. So every time you contract this gastrocnemius, you pump more blood back to the heart. Now this is why with Starling's law of the heart, that very well-conditioned athletes have a high end diastolic volume. because their muscles are so toned that they return blood to the heart very efficiently. And in between beats, their end diastolic volume is very high. So this is one of the functions of skeletal muscles in helping us return blood to the heart, venous blood to the heart. This is a pie chart showing you where all the blood is at any given time. At any given time, all of the blood is here in our veins. All right, you don't have to memorize which. Please don't even memorize the numbers. I won't test you on these numbers. This is about 63%, I think. 25 and 21 is 46. By the way, I said just don't memorize the numbers. I'm going to give you the number. I'm just going to give you the number, but don't memorize it. 25 and 21 is 46. 46 and 18 is 63. Yep. Oh, actually, it's telling me right there. I don't know how I did that wrong. 64%, right? 64% right there. At any given time, most of your blood is in the veins. Now, your capillaries have the greatest cross-sectional diameter of lumen, but remember, at any given time, the blood's not in your capillaries because at any given time, more than half your capillaries are shut down. So at any given time, most of your blood is in your veins. And that's just a snapshot of time. You can see that at any given time, only 7% of the blood is in my capillaries. And that's because we shut more than half of them down at any given time. And then it shows you the arterial systemic circuit and the pulmonary circuit. And again, don't memorize these numbers. Just realize one thing. Most of the blood is in your veins in a given snapshot of time. All right, that's the blood vessels. See you in the next section.